Close your eyes and travel back 13.8 billion years to an age when the universe was not stars and galaxies, but a glowing fog, hotter than the core of any star and thicker than the heart of any cloud. In that infant plasma, faint sound waves rolled like pulses on a drum. Their crests were only 1 part in 100,000 higher than their troughs, soft enough that no human ear could ever hear them, yet loud enough to write the opening bars of the cosmic symphony. Ordinary matter, protons, electrons, newborn light was caught in a tight embrace. Radiation tugged it outward, gravity pulled it back, and the two forces traded blows 250,000 times per second. But something else floated in that fog, something immune to light's push: dark matter. Cold, transparent, and already abundant, felt nothing but gravity's tug. So while photons kept ordinary matter jittering, the unseen mass began falling inward, deepening each ripple into a hidden well. By the time the universe cooled enough for atoms to form, the fog cleared and light escaped, carrying with it a fossil picture of those ripples. The map we now call the cosmic microwave background. Yet the true architects were the invisible wells beneath. From those roots, filaments of dark matter thickened, and in their valleys future galaxies would one day ignite. The lesson is quiet, but profound. The first structures were laid not by starlight, but by darkness. Next, we'll watch computers rewind and fast-forward this hidden history, revealing the foam-like scaffold on which all galaxies hang. Step into a chilled data hall where blinking lights replace starlight and processors hum like distant cicadas. Here, supercomputers play the universe in fast motion. Feed them simple ingredients: gravity, the measured amount of dark matter, the faint ripples we met a moment ago, and press evolve. What begins as a faint fog of particles quickly stretches into gossamer threads. Nodes thicken into knots. Knots merge into titanic hubs. Between them, vast voids balloon like soap bubbles. This is the cosmic web, a foam hundreds of millions of light years across, yet as delicate as frost on glass. And the stunning truth is that the simulation needs no stars, no supernova, no chemistry to craft this scaffold. Gravity pulling on invisible mass is enough. The dark matter streams together, slowing only where filaments cross. Ordinary matter allowed into the program later merely flows downhill, lighting the junctions like neon tracing a city grid at night. Fly through one of these digital universes and the view feels eerily familiar. A spiral of threads, not unlike neurons in a human brain or roots beneath an ancient tree. Rotate the camera, and patterns echo across scales. Small knots orbit larger hubs. Narrow bridges feed them both. The correspondence with real sky surveys is so striking that astronomers now use these virtual webs as laboratories, tweaking the amount or temperature of dark matter until the simulation's foam matches telescope charts. And yet, in the corners where the code falters, where dwarf galaxies misbehave or spiral arms twist too soon, wait clues to physics we do not yet know. For if gravity and darkness alone can paint most of the canvas, the imperfections hint at finer brushes still missing from our kit. In the next chapter, we'll watch bright matter fall into these invisible valleys, discovering how stars, spirals, and supernova merely gild the skeleton built by dark matter's silent hand. Picture a dark matter halo as a vast but unseen mountain range. It rises in silence, crag upon crag, until gravity deepens its valleys so far that even lightless particles slow their drift. Into those invisible basins, ordinary matter, gas laced with the first atoms, begins to rain. At tens of thousands of degrees, the gas is restless, but as it tumbles, it sheds heat the way a runner exhales steam. Cooled, it pools at the center, spins and flattens into a luminous disk. Switch on the cosmic lights and a spiral galaxy appears, its starry arms tracing the skeleton beneath. Yet the glow does not simply settle, it converses with its dark foundation. When newborn stars detonate as supernova, they hurl gas outward like ash from a campfire, momentarily thinning the spiral arms. Supermassive black holes and galactic cores can do the same, launching jets that stir the surrounding halo and quench future starbirth. In quiet suburbs of the universe, where halos grow steadily, These heated cycles leave the disk intact, and grand design spirals, such as our Milky Way, emerge. Where the dance is rougher, two halos collide head-on, or several jostle in a swarm, the disk shatters into streams. Stars scramble, gas shocks and heats, and the system relaxes into a bloated sphere, an elliptical galaxy, glowing like a cosmic ember. Astronomers now replay these dramas in supercomputer theaters, tuning feedback from supernova and black holes until virtual galaxies sparkle and puff in the same ratios telescopes reveal. So when you gaze at a whirlpool of starlight, remember, you are seeing only the frost along a hidden spine, sculpted by gravity's quiet architect, dark matter. But even master sculptors leave imperfections, and in the smallest corners of the sky, those flaws may expose secrets we are still struggling to decode. Zoom far inside a computer simulation of cold dark matter, and you find halos within halos. A city of skyscrapers surrounded by suburbs, each suburb orbited by villages. The numbers are breathtaking. Thousands of small clumps should twinkle around every big galaxy. Yet when astronomers sweep the real sky with giant telescopes, they find only a few dozen faint dwarfs circling the Milky Way. This missing satellites gap is the first whisper that our cosmic blueprint may need fine print. Look even closer. Simulations predict that dark matter density should spike sharply toward each halo's heart, forming a cusp. But surveys of dwarf galaxies show gentle cores, densities that level off like the summit of a worn-down hill. And some of the simulated subhalos are so massive that if they existed, they should host bright dwarfs too big to fail at making stars. Yet the sky is quiet where those giants were forecast. Are these cracks in the cold dark matter idea, or is ordinary matter to blame? Supernova winds can blow holes in cusps, puffing cores into existence. Reionization, when the first stars bathed space in ultraviolet light, may have stripped gas from many baby halos before they could sparkle. Others posit warmer or self-interacting dark matter, particles that blur or bump just enough to erase the sharpest peaks. Each puzzle is an invitation. Adjust the particle, refine the feedback, or rethink gravity itself. The cosmos has left us a trail of mismatched footprints. Follow them and we may stumble upon dark matter's true identity, or an altogether new path through physics. To choose between rival answers, we must probe deeper. Weighing particles against paradigms in underground chambers and radio-quiet valleys, that journey begins in the next part. Stand beneath a rural sky, free of city glow, and let the Milky Way arch overhead. A river of starlight steady as ancient myth, it feels complete. Yet every piece of evidence we have gathered, spinning disks, colliding clusters, the infant hiss of the cosmic microwave background insists that most of this river is an invisible current. We can chart its pull, model its architecture, even watch it shepherd galaxies through time, but we have never cupped it in our hands. At this crossroads, two roads diverge into the dark. One says the unseen mass is a new kind of particle, quieter than neutrinos, colder than the cosmic night, lipping through detectors like ghosts through walls. Find that particle, catch its rare collision in a pool of liquid xenon, or listen for its faint conversion to microwave tones in a whispered quiet cavity, and the puzzle locks into place. The equations of gravity remain pristine. Only the ledger of matter grows a new entry. The second road is bolder. Perhaps there is no missing mass at all. Perhaps the law of gravity itself veers from Newton's verse, when the lights grow dim. Tilt the equation just a hair, and galaxies stop demanding dark companions. Some versions, Mont, Teves, emergent gravity reproduce rotation curves with elegant economy, yet struggle against lensing maps and the CMB's acoustic drumbeat. The debate is no longer about numbers. It is about the very grammar of the cosmos. Which path is true? The answer awaits in shafts carved deep beneath mountains, in radio dishes that sip the galaxy's static, in particle beams and precise orbital clocks. We stand on the threshold, poised to weigh the ghost itself or rewrite gravity's oldest poem. In the next part, we descend into those caverns and climb into those towers, pitting particles against paradigms in a bid to illuminate the darkness once and for all.